So this unit is on probability. And before we get started on probability, I think the nice thing about this is you all have a bit of an understanding of probability. If you think of any time you've played a game and you were rolling a dice, that you shake it in your hand and you think to yourself, I need a 6, I need a 6. What are the chances of me getting this 6? This has to do with probability, the chances of something happening. Okay? We'll look at a couple of definitions. Theoretical probability, that's right here, is the number of favorable outcomes divided by the number of possible outcomes. Now that's a fancy way of saying it, but that's all it means. Okay, if you look at it down here, maybe that makes a little bit more sense. The number of favorable outcomes over the number of possible outcomes. So thinking about some everyday scenarios, what is the probability of rolling a heads on a coin, or flipping a head? So you take a coin and you flip it, the chance of getting heads is 1 out of 2 possibilities. Okay, the probability of rolling a 4 or a 6 or any other number on the 6-sided die, there's 1 favorable outcome out of a possible of 6. Okay, what is the probability of getting an ace from a deck of cards? Well, how many aces are there? There are 4 aces in a deck. How many cards are there? So this is the total number of cards. That would be 52. Okay, what is the probability of rolling an 8 on a 6-sided die? Well, there are no 8s. So this is 0 out of 6. And what is the probability of rolling a number that is less than 7? Well, all of the numbers are less than 7, so that's 6 out of 6. Okay, so that's a kind of an introduction to theoretical probability. Experimental probability is when you actually perform whatever the task is, and it's what actually happens, not what might happen, but what actually happens. Okay, so let's try a few questions. Oh, sorry, not quite. We're not quite done here. All probabilities must be expressed as values between 0 and 1. So if you look at all of these numbers here, okay, what's the biggest number that you have? The biggest number would be 6 out of 6, which is 1. The smallest one would be 0. Probability can't be less than 0, and it can't be greater than 1. So it's always going to be something between 0 and 1. That's what this means. Okay? And then we have something called the complement of a probability. The probability that an event does not occur is the complement. Okay, so let's look at an example. For a 6-sided die, the probability of rolling a 5, that's 1 out of 6. The probability of not rolling a 5, well, you can already see that's 5 out of 6, but looking at our formula here, the probability of not rolling a 5 would be 1, take away the probability of rolling a 5. So 1 take away 1 over 6, which if we do the math here, this is 6 over 6 take away 1 over 6, you end up with 5 over 6. Okay, so that's what the complement is. It's the opposite, sort of the opposite of something happening. Okay, a few questions here. When rolling a normal 6-sided die, what is the probability of rolling a 7? Well, we already know there are 0 possibilities. So, not out of 7, out of 6. Okay? When rolling a normal 6-sided die, what is the probability of rolling an odd number? Well, the numbers that are odd are 1, 3, and 5. So that's 3 favorable outcomes out of 6. Okay, when rolling a 9-sided die, so there are 9 possibilities, what is the probability of not rolling a prime number? Okay, well, first of all, we need to know what a prime number is. A prime number is any number that can be divisible by 1 and itself. So 2 is prime, 3 is prime, 5 is prime, 7 is prime. All of the other numbers between 1 and 9, like 1 only has 1 factor, and all the other ones have more than 2. Okay, the prime number only has 2 factors. So this is the probability of a prime number would be 4 out of 9. So what's the probability? I'm going to write it in a different way here. What is the probability of not a prime? So this is 1 takeaway 4 out of 9, which is 5 out of 9. Okay, a bag contains 5 red, 4 black, 3 green candies. If you add those up, there are 12 possibilities. What is the probability of not selecting a black candy? Okay, so first of all, we should say, what is the probability of black? So what is the probability of not selecting a black candy from the bag if one candy is randomly selected? So what is the probability of black? It's 4 out of 12. So what's the probability of not black? Well, this would be 1 takeaway 4 out of 12. Okay, and that's 8 out of 12. Okay. Now, just going back here a little bit, this is one way of writing not something. We have that solid line over. I've also seen it with B prime like that. Okay, either of those is fine. Okay, what is the probability that there will be 2 girls in a family with 3 children? Use a tree diagram. Okay, so first child, second child, third child. So the first child could be a boy or a girl. Second child could be a boy or a girl. And the third child could be a boy or a girl. Okay, so listing all of the possibilities here, we have boy, boy, boy. We have boy, boy, girl. Boy, girl, boy. Boy, girl, girl. So I'm just following these. Okay, and then the next one would be girl, boy, boy. Girl, boy, girl. Girl, girl, boy. And girl, girl, girl. We're supposed to look for what is the probability that there will be 2 girls. Okay, so that's 2 girls. Here's 1. Here's 2. Here's 3. The probability of 2 girls is 3 out of 8. Okay, so now let's get into experimental probability. I would like you to try an experiment. Now everybody's going to have different answers here, so the notes are going to be a little tricky. But what you're going to do is use 3 coins, okay, 3 pennies, dimes, nickels, or whatever, to represent the 3 children, with heads representing the girls. So if here's your 3 coins. If 2 turns out head and 1 turns out tails, this would represent 2 girls and 1 boy. Okay? So what you're going to do is toss 3 coins 50 times. And each time you record what you get. So if you end up with 2 heads and a tail, you would put a tally mark here. If it's not 2 heads and a tail, you would put a tally mark here. Okay, and you're going to do this 50 times, whatever you end up getting, I don't know. Okay, so go ahead and try that. And once you've done that, you can unpause the video and then come back to this. Okay, so experimental probability, whatever you had here, that's the number that goes on the top. Whatever you had here, plus, if you add these two, okay, this is going to be 50. So then we're going to figure out what the experimental probability is. Now, we already knew the theoretical probability was 3 out of 8, which is about 0.038. Okay, compare the experimental answer. So what is your experimental answer? Is it close to this or is it far away? All right. I had expected it would be fairly close, but it doesn't have to be. It could be off a little bit. The point here that we should make is, do you think your answer will get closer to this number when you do more trials? So instead of doing 50, if we did 100 or 200 or 1,000. So this is the case. The more trials performed, the closer the experimental probability will be. To the theoretical probability. Okay, so what that means is if we do this trial over and over and over again, eventually our experimental probability will be very close to what the theoretical probability is. This is a really good lesson to learn. Have you ever played a game where you're rolling a die and you've, say, rolled 6 in a row, and then the person you're rolling against might say, well, there's no way you're going to roll 6 again because you just did it a whole bunch of times. Well, you realize that even if you rolled 6, like 10 times in a row, which is very unlikely, that next roll, what is the chance of rolling a 6? Well, just because you've done a whole bunch of 6s does not change this. This is still a 1 in 6 chance of rolling a 6. Theoretical probability is a better gauge of what the actual probability is. Experimental probability is what happens, and sometimes what happens is weird, but the more you do it, the more likely it will be closer to the theoretical. Okay, so it's important to keep that in mind. Let's talk about what a fair game is. A fair game is a game in which all the players have an equal chance to win. Okay, for example, if we both have a coin, and if you get a tail and I call heads, then we have a 50-50 chance of winning. We both have an equal chance of winning. Okay, so let's take a look at this game. I want you to take a look at the game, read through this, and decide, is the game fair? Okay, so pause the video, read through it, decide, is the game fair? Okay, so you're back, and hopefully you've decided. First of all, if I just play the game once, is that a good way to decide if it's fair? No, it's not. Okay, the best way to determine if it's fair is to use theoretical probability. In other words, what should happen if we do this? Okay, well, let's take a look at what should happen. Here are the results. So this is what, if you take two coins, or sorry, if you take those pieces of paper, all right, these are the possibilities. We could pull out a 1 and a 1, so we could pull out a 1 and a 1, and the product would be 1, and the sum would be 2. Okay, and these are all the possible things that could happen. All right, and you can see that what? If both numbers are 1s, player 1 wins. If we have a 1 and a 2, player 1 wins. If we have a 1 and a 3, player 1 wins. These two places, player 2 wins. And then there's the tie. So is this game fair? Well, you can see that player 1 has a better chance of winning. Player 1, so the probability of winning for player number 1 is 5 out of 9. For number 2, the probability of winning is only 3 out of 9. Okay, so that's how you determine if a game is fair. So, question C is, when you play the game, would you rather be player 1 or player 2? Well, assuming you want to win, you'd be player 1. Okay, here's your homework for this lesson. Okay, good luck with that. Let me know if you have questions.